So till now, you must have used NumPy for doing the computations and all, like any kind of matrix multiplication, or let's say in machine learning models, you whatever required, mostly done using NumPy. If you start to write the code of any model from scratch, you might require NumPy to do the computation, and that is good. Like NumPy is a good library; it has everything, whatever you require. But the issue comes up when the deep learning comes as that there is a huge amount of data, and doing this computation using CPU uh, was the bottleneck of this. So we required something which can elevate from that bottleneck. That if I have some tool which can handle this huge computation, so for that, first the architecture comes in that the engineers build GPUs. So what GPUs does is it can parallelly do the computations, and that's what reduces the time for that computation, right? So to actually use the GPU, we require some framework which can do that. That frameworks are in terms of our scope, like deep learning scope. There are two kind of frameworks which are popular. One is Pytorch, and another is TensorFlow. Okay, there is no difference between like is there anyone better than the other, or is there anything? Like, are they like? But they do exist. Okay, so there is no certain amount of text. There is no significant difference between them. It's just they can be written in different ways, and they have been built by or developed by different kind of developers. Right? So the TensorFlow is developed by Google, and this PyTorch is developed by Meta. Okay, that's what the pretty much difference is. But so I use both of them, PyTorch as well as TensorFlow. And what I've realized is PyTorch is kind of very similar to the NumPy. So if you have done NumPy, if you've used NumPy before, you'll feel that most of the codes or whatever functions are written are kind of like NumPy. So that's good. It's relatable to NumPy. TensorFlow won't be like that. It is a little bit different, and all. Okay. Now, another plus point of PyTorch is that most of the research paper, if you come across any research paper, uh, highly likely that they've used PyTorch as a framework to explain their research work. Okay, so in terms of like education field, PyTorch is more popular than TensorFlow, and TensorFlow is more popular in industrial fields. So if you go to industrial, right, so that's where TensorFlow is popular. But in terms of research field, PyTorch is popular. But now this trend has kind of whatever I'm saying might be changing also. The reason is now this Chat GPT came, right? So this Chat GPT is using PyTorch. So Chat GPT was built on PyTorch, and several more LLMs. Since ChatGPT was the pioneer of this transformers thing, so other frameworks or other this LLMs which are coming, they are highly likely to use PyTorch as their main framework to build that, right? So that is the idea. Like and research related to ChatGPTs are happening. Everything around this LLM has changed a lot, and due to this one LLM, there is a high demand of PyTorch, which is increasing, right? And later on, you will use something called Hugging Face. If you take DLP course, so DLP course is mostly you will come across Hugging Face in that. Hugging Face is another library. Uh, like I'll not go into this, but I'll just show you that Hugging Face is something. Not this one, right? So this is another library which is useful for transfer learning and such things like that. And so most likely this Hugging Face models which are given here for transfer learning are supported by PyTorch. and the documentation of you will be able to find. Most likely they are in the Pytorch only. So that is also one plus point a Pytorch has. But still, industry people use TensorFlow, and it's been working like that. So it's there. Okay, so some benefits are there, and some maybe drawbacks would be there, but that's okay. It's negligible. Okay.
Hello, sir.
Yes.
Just like sklearn, which implement ML algorithms, the
Hmm.
PyTorch and TensorFlow implement the deep learning algorithm. Am I right, sir?
Yes.
And in DLP course, we will learn PyTorch.
Uh, you will not learn the Pytorch there. Uh, so you'll use Hugging Face. So this Hugging Face is another thing. So okay, with DLP, I don't know, but the thing is there are three things: text, speech, and image, and you will require some pre-trained models to do the work there, right? So this pre-trained models, how will you get is Hugging Face is the one who will give you this pre-trained models. Okay. Um, so you don't have to build the models from the scratch, and that's what Hugging Face is ensuring, that you don't have to build it from scratch. But building it from scratch is useful. The
But
reason is
sir, Hugging Face, the models give is LLMs they give, right?
not necessary. So there are image models also there. So what? Not sure, but see this video classification. If I go, so whatever these models are, they are going to be video based model, right? So something, it's not necessary that it will give you text or transformer kind of models only. All kind of are available. Even speech models are also there, right? So this computer vision multi-model, uh, then NLP is there, audio, tabular, reinforcement learning, then something on other side. I'm not sure what is it, but it's there, right? So everything is there. It's not necessary that only text is there. Okay. Uh, okay. Now we'll move ahead. So now we'll understand what is tensor, and so here the tensor is something which is n dimension. Okay, so anything which is n dimension, you can call it as tensor, and tensor could be a scalar value, it could be a vector, it could be a matrix. This is the 2D tensor is called the matrix which we generally see is a 2D tensor. 1D tensor is a vector, right? So you have seen the vector like y labels and all are 1D tensor, and 2D is a matrix, weights and all, and 3D tensors are having a, you can say, length, width, and depth also, right? So the image data would be a 3D tensor. And similarly, if you stack up the 3D tensors like this, like let's say, so this individual unit is a 3D tensor, that becomes a 4D tensor. And similarly, if you stack it up like a, um, how do you put, across like width-wise and uh, height-wise, then that becomes 5D tensor. And similarly, if you put it like this, then it becomes 6D tensor, and it can go to any dimension. Okay, but we don't have to worry about it. Like the highly or the highest, maybe if you go with any kind of problem, mostly you will be able to solve using 7 or 8D tensor. You're not likely to get anything more than that. Okay, so it's possible, but you will not require it. And okay, so now
So how is it different from a matrix? I mean,
uh,
from
it is
any.
it is not a difference. There is no difference between matrix and the tensor. So this 2D tensor is same as matrix, or it's just the name is used as tensor. Okay. Uh, the only difference between this tensors here is they support GPU acceleration. So you can do computation in GPU now using this tensor. But if you make a NumPy array, right? So this NumPy array, if you make, then that doesn't have any GPU component to it. So you can't do any GPU computation using this. But using this PyTorch tensors, you can do it. Okay. So like both NumPy arrays and tensors are multi-dimensional arrays. That's what it is. Um, uh, okay. And what, I guess there is some mistake. Uh, Now what a tensor can do is it can do GPU acceleration. So that's what it is. And something called automatic differentiation. We'll cover this. What is this automatic differentiation? That is a very important component of this, the whole deep learning models that we are going to create, the CNN, ANN, RNN. Because you know that back propagation is the backbone of all the models, and we to ease up the back propagation, the tool which is developed by this Pytorch and TensorFlow, or for now I'll just talk about Pytorch, that the differentiation will happen automatically. So something we'll see. Okay, what is this? But just remember that the differentiation happens automatically if you move forward. So let's say 2x. If you send 2x, then it knows the differentiation of 2x is going to be 2. Okay, like that. And then something like tensor computation. So this tensor computation, okay, so this like matrix multiplication or any kind of addition, multiplication, division, all kind of things are under tensor computation. GPU, okay, dynamic computation graph. We will see that also while we doing this automatic differentiation. So the thing is, it will make a graph of the structure, that how it's going in the forward direction, right? So that will help in remembering that from which path the gradients are coming, and then that's what the computation graphs are being made, and it will help while doing the back propagation. So this forward propagation happens in a kind of graph function, a graph kind of thing, and that's what helps in back propagation. So this part will also will do when I'll explain this automatic differentiation. So this too we'll see. Now something called distributed training. So uh, so this is like, let's say you want to do matrix multiplication, right? So generally what you do is you first multiply one thing, then go to next thing, then next thing, right? So that is what it is. But here you can do, you can divide the load and do the training itself, right? So um, so let's say you have a huge image data. You don't need to take all of them. You can take a few images and then create tensor and then do the training, something like that. So this all kind of supports are there in PyTorch, and we'll see how we can do that. Okay, so but this all things are there in PyTorch. Now okay, I'll go with this explanation a little bit. So let's say zero dimension tensor, like scalar value. You might see loss value as a scalar. Okay, so let's say mean squared error or cross entropy, those things are always going to be scalars. Just remember this, because sometimes you might make a mistake in doing forward propagation, and if loss value is not coming out as a scalar, then the back propagation will not happen, because it's expected to have a loss function as a scalar. That's why I'm putting a little bit weight here. Then one dimension tensor, let's say word embedding, word is being represented as a vector or something, right? So n dimension vector, or you can say labels are also kind of vectors. Then two-dimensional image, grayscale image. So something like this, a grayscale image looks like. It has values from, depends on what kind of grayscale you're using. From 0 to 255 could be there, or it could be less. So those value, whatever value in that pixel is, that's what gray image is. And then if you add channels to it, right? So 3 channels is the RGB channels are there. So when we'll do this image classification using CNN, we'll come across this again, that what are this RGB channel, how does this 3-dimensional tensor looks like. But just remember that whatever this grayscale thing is there, you can think like we'll add 2 more layers to it, maybe one after another, right? So one is front, then after that, and then behind that. You can imagine like that. So that's how this 3-dimensional tensor will look like. And so we'll do batching of this, right? So we'll create image. So we'll have images, and we'll create batch of that image, right? So we'll not be able to use all the images together. Maybe that is like limitations of our computational power and all, several reasons. And we'll do always batch training, right? So batch stochastic gradient descent, something like that. So if you do that, that becomes 4-dimensional tensor. So you'll send maybe a batch of 32 with this 3 things, right? Channel, width, height, and all. So same thing, like if you have 5-dimensional tensor, then you'll send batch, then frames also you will send, then width, height, same thing. So this video sequence will be like this. And then 6-dimensional tensor, like multiple video clips you'll send, like, so one clip is there, then another clip, then third clip. So this is, I'm talking about one video, but if you have multiple videos, then you might need 6 dimensions. And there are several 7 and 8-dimensional examples also, but you don't need to, uh, generally will not use as of now. If it come across, it's just one more dimension. Okay, that's what you can think, that if you have matrix, there is one more dimension. If you add it to it, it becomes that dimension tensors. Okay, 3D, 2D, 4D. So generally, as of our course or our workshop, we are concerned about this 5 kind of tensors from 0 to 4 dimension. So this 4 dimension will come when CNN thing when we'll do this batch with height channel will be there. Okay, so this 4 kind of, as of now, we are concerned about. Now, so where we'll require this tensors, right? That requirement will be like, so this training data, right? So storage and representation. So whatever of training data is images, text, if it's a ANN, then or maybe let's say tabular data. So metrics. So this all representations in numbers will use tensors. So now, whenever I say tensor, just think that it's a Pytorch, um, n-dimensional array. Okay, so array is the term, but now I'll use tensors for that. And whenever I use tensors, it could be of any dimension. So generally, maybe if possible, I'll mention the dimension, but just consider it's a some dimension array. Okay, not something different like, I don't know what else, but it is a array. Okay. Now, parameters we might wanted to store as a tensor. So weights and biases, gradients. So when we'll do back propagation, these gradients will get. So this gradients we have to store in a tensor. Okay. All the mathematical operations which we are going to compute in this 4-day workshop are all going to be tensors. So you can do addition, matrix multiplication, this all things you can definitely do using tensors. So that's what this tensor is. Okay. Now I think I'll connect this thing. Okay. So before I yeah, few things which I wanted to mention is, so if you don't know, you can go to this change runtime and you can select this T4 GPU. Not now needed. I'll connect it later, because there is some limitation to it. Like I think I can use it for maybe 2-3 hours or something like that. I'll not connect it now, but we'll do it later. And whatever GPU I have is being built by NVIDIA, and there's something like CUDA, which they use to do this parallel computing, right? So that's what this NVIDIA built it, and that's why this NVIDIA was very popular in this past many years, right? Until this DeepSeek came, but nonetheless, it is still popular. Okay. Parallel computing platform, and programming model, whatever programming which is required to do this parallel computing was built by NVIDIA, and that's what we call as GPUs, right? So this CUDA is the one, this computing platform and programming written by them, and GPU is the unit which we call it. So the code which you have to write to import the PyTorches, you have to write import torch. So if you write this and if you run it, it will get imported. Okay, so there is no, if you are using Colab, then there is nothing you have to do. Otherwise, if you are using Jupyter or something, maybe you will require maybe pip install torch and all into your local system, right? So check it out how to install it. But I'm using Colab as of now, so which has already pre-installed it, right? So I don't have to pip install things this torch. Now, just for the sake of doing, I'll just check which version we are. Okay, so we are using 2.6 of this PyTorch version. Okay. Now, so these are a few modules which will come into the PyTorch sessions which we are going to cover. And you don't need to remember this now, but it would be great if you just know it. Okay, so of course you can always search about it later, and you'll be able to figure out what you have to do, right? So I just zoom it a bit and bring it. So this torch um, okay, so one module is torch, which we have imported, the import torch. So this is a core module providing multi-dimensional tensor mathematical operations on them, right? So this is a basic library, like a NumPy, import NumPy as NP. If you do that, that's what we are doing as a torch, import torch. Okay, there's nothing new about it, just arrays and all this basic functionalities it will give you. Then inside that, some modules like AutoGrad. AutoGrad will be the automatic differentiation engine that records operations on tensor to compute gradient for optimization, right? So this gradients computation and all, remembering which path you are going. So this computation graph which I was talking about, this all will be carried by take care by this AutoGrad. Okay, then this NN module will come. So this is the most important uh, module in this, or you might will use this lot of the time. So you'll not use AutoGrad because it's there, but it's like we don't have to do it. Okay, it will be automatically done. And this NN is the one which will use several times to build the model. So you can see it provides neural network libraries. So this layers which we are going to define, right? So in ANN we have hidden layer, then softmax layer, ReLU, sigmoid on top of a layer. So this activation functions, this all will be available inside this NN module. Just remember that NN module loss functions are also there, and some other utilities to build deep learning models are available in the NN module. Then there is something called Optim. So all the optimizers which are taught in the deep learning course will be available in the Optim module. So few of them are like SGD, ADAM, RMS Prop, NADAM, or even further which are being researched are all available in the Optim module. Okay. Then there is something called utils.data, which has two main important functions. One is called data set. So this data set is a function as of now, and this data loader another function or class. If I say correctly, it's a class which we are going to use, which we are going to definitely use, and these two classes are important part in this utils.data. Then something called distributed tools for distributed training across multiple GPU and machine facilitating parallel computation. So this all things are available, and you will see that we'll not likely to use this distributed CUDA multiprocessing quantization. On ONX we will use this. So this one another like important module. So it supports exporting the PyTorch model. So let's say you have built the model, you want to store it, right? So that storing, and if you are building a website, you want to put it there. So this all you can do using this ONNX, right? So Open Neural Network Exchange is a format which it uses to create the model, and you can store it, right? So uh, for interoperability with other frameworks and deployments. So if you want to do the deployment of the model, you want to use it, right? So REST 3 does exist, but not much useful. Now there is something called Torch Vision, which we'll use when we'll do vision classification. So image classification and all, video classification, that kind of thing you can do. So few of the libraries will be available there, like this. So this several things are there in this itself. If you have text data, then there is another module available inside the Pytorch for text only, right? So if you are dealing with the text, then you can see get tokenizer, ngram, text classification, something like vocabulary, transformations, right? So few transformations you might wanted to apply before training it. So this all things are available in text. If it's a text data, then you might wanted to go into this. For audio data, there is another thing. Okay. So this all things are there. You don't need to remember any of this as of now. You just need to know that this all exists, so that whenever you are going to build a project, you can think of it. Okay, so that this all possibilities are there, and you can use whatever is required. Okay. Yeah. So that was kind of a theory of it. What is a tensor and all. Now we'll do the practical implementation of that. Before that, any doubt? So
Sir, in today's lecture, in these 4 days, can you distribute the our DL course week wise so that we could revise again for that?
So today we will not cover anything which is likely to come in the DL course, but tomorrow we'll do this ANN part. Uh, right. So this ANN part, for that you will require to know the forward propagation, back propagation of ANN a little bit. So idea about that will be good, and after that we'll do CNN. So that's where you should know CNN architecture. How does it work? And most importantly, the important part in CNN you should know is how to calculate what are the dimensions you are going to get after convolution operations, right? So let's say 256 or 256 dot image you applied 3 cross 3 filter. Now what is the output dimension? So that's something you should know, how to compute that. It is going to be useful for building the CNN, right? And another is how many parameters are there. Not necessary, but this output thing is the most important thing about thing. And then of course RNN, how does it work? That's what you would require. So this backprop and all not required in this. Yeah, both of them. You don't need to know back propagation, but in ANN you should, if you know the back propagation, would be good. Like it will become easier to understand, and once you get the hang of it, that how the back propagation happens using this automatic differentiation tool, then you don't need to actually know the back propagation of CNN and RNN. You just kind of believe it that it's going to work. Okay. Yeah. So uh, tomorrow and day after that, so this 3 days you have to um, learn these three things, like, related to the DL course. Uh, yeah. Anything else? Yeah, go ahead.
Sir, you released like a YouTube playlist, right? For like the if you understand that, that's more than enough to understand whatever is happening in the workshop, no?
Uh, yes, that is correct. So till
Oh,
CNN, it's there.
yeah, tell
Uh,
CNN is not there.
the RNN will cover on the last day,
No, no,
but yes, that is
uh,
correct. So
that
if
is enough.
you follow that playlist, that is also okay.
Okay. No, but that and this are same, or that's like a prerequisite is what I'm asking.
Both are same.
Okay. Thank you.
Yes. Okay. Now, okay. So now we'll start coding, and we already imported Torch, so I'll use that. So as of now, we'll just learn few things about like how to create tensors and all. Okay. Just in case you like this in a light mode or dark mode.
Sir, whichever you find well, sir.
Oh, no, sure. I generally use dark mode, but
So light mode is good for video, sir.
yeah, for video and like student uh, do in like they like light mode, so I do that. Okay. Now, how do you define a tensor? Is you have to write torch dot tensor, okay, and then you can give a value. Let's say 2. If I write, that is a tensor, and then I have to store it in a variable. So let's say this is my first variable, okay, like this. So this is my variable, and what I have stored is 2. So 2 means this is a scalar tensor. Okay. Now if I show you the first, like so it's coming out of a 2, and you can see tensor 2. So it's not a numpy array or just array. So we are kind of moving away from the arrays terminology. It is array, or you can say metrics and the scalar and all. But now we are going into the tensor. So this terminology tensor will definitely come up lot of the time. Right? Now let's say you want to see that what kind of tensor it is. Is it a scalar? Is it a 2D, 1D, 4D? What is it? So what you can do is you can use this ndim function or ndim functionality of this tensors. So you have to write like first variable dot ndim, and if it is giving 0, that means it's a scalar tensor. So let's say if I create another tensor, like let's say I'll call it as a, and I like torch dot tensor, and if I give a vector to it, let's say 2, 3, 4, 5. So this is a vector I'm giving, and if I print or show the a, it's a tensor and it's a vector. Now if I write a dot and diff, right, you can see the value is 1. So this is the dimension of the tensor. If I wanted to check it out, I can do using ndim. That is the way. You can definitely use shape also, like a dot shape, and like, so here you might have to think like, what is it like? Is it a vector or something? So if it is a matrix, it will become easier to maybe understand. Let's say if I do, say if I have b and torch dot tensor, let's say a matrix 1, 2, and then 3, 4. So this is a 2D thing, right? So b dot and dim. So it's a 2-dimensional tensor, and b dot shape. Okay. So this will give you 2 cross 2. So from this also maybe you can figure it out that it is a matrix. So just don't see 2 cross 2. That has nothing to do with the dimension. For example, you just add one more value. Okay. Yeah, something like this. So, yeah. So this n dimension will be useful for finding dimensions. You can create tensor like this. So just remember that whenever you need to create a tensor, you can do this way. So this is a creation of tensor. Now another thing which will come up is what kind of data type this tensor is holding, right? So you can see this whatever we have created as of now, like this 2 is an integer value. This all the values are integer. Here also all of them are integer. So the possibility of dimensions or sorry, possibility of data types are integer, float, and what else could be there? Double, short, long. Okay, so this all things are there. Now, okay. So I'll just explain it. So what we do is when we store the values, we use something called like a bit coding, right? Like let's say I want to store a number, let's say 1, and I can do using 1 byte, right? Or either 0 or 1. If I wanted to store 2, what I can do is I can use 0, 0, 0, 1, right? So this way I can store um, value as 2, right? So this is like how bytes or bits are being made. And so to store a value, you can use how many bits required, right? So maybe it is always going to be multiple of 2. So maybe 2 or 4 bits or 8 bits or 16, 32, 64. So till 64, as of now, all the values present in the uh, like all deep learning can be stored using 64 bits. Okay. So for example, what I mean by that is, so if I see b dot d type, it is int, most likely 64. Okay, this, yeah. So this torch dot int 64, which you are getting here from here, right? So it could be 32 also and 64 also. So the more you choose this value, the higher memory you will require, right? So the bits which are in the memory, kind of you can maybe imagine like this. So like this, these are 4. Like that, you will require 64 of them to store one value. Okay. So 64 bits will be required to store value, and if it's a value is less than something, you can maybe have less than like 32 bits are sufficient to do it. So the most popular bits which or with the most popular data type which we are going to use in this course is float 32. Okay, so the float torch dot float 32. Just remember that this is the most popular data type which we are going to use. The reason is most of the models which we are going to make, for example, ANN layers, CNN layers, and even RNN also, and after that also, right? LSTM, GRE, whatever you can go up to, they are built in such a way that they support float 32 as the input. So if you give, let's say, integer 32, even though let's say 1 is a integer 32 value, if it is possible, still it will not work. You have to give 1.0. Okay. So just remember that this data type is very important when you create a tensor. You have to mention what data type you are going to create. So that's what we'll do. So let's say if I create a tensor, let's say a torch dot tensor, okay, and my tensor is, let's say, 1, 2, 3, like this. So I need to mention what is my data type going to be, right? So that I can write d type, and I have to write torch dot, it's a float 32 a. If I show you, it's still the same value, maybe which I have stored here. It's just this a has all the integer value, and here it is float value. You can see one dot here after each number, and that's what it is, like a dot. Of course, I mentioned here, so it's going to be 32 only. Still let's do this. Okay, float 32, and that's what supported mostly. Now this double, short, long are coming into this. So if I show you this documentation about that would be double Pytorch. This d type Pytorch. Okay. Yeah, So here you can see that 64-bit floating point is a torch dot double. So there is nothing different between torch dot float 64 and torch dot double. So this both of them are same thing, and what it represents is 64-bit floating point number. So if you see double somewhere, don't get confused. If you give half or float 16, they both are same. And maybe you got the idea that if you by default use torch.float, it will going to create float 32. Okay, so this is the default one. Double of that is 64, and half of that this 32 is 16, right? So that's how this namings are coming up. Then there is one more important one is long. So this long is integer 64. So this long will be useful when we have labels. So just remember that whenever you have labels, try to encode it with torch.long or int64. That is also, kind of all the models which are being built in this Pytorch framework. They kind of expected that the labels I'm going to get are going to be in long D type. Okay, so this few things you have to make changes, and that's what it is like. Data types does exist, and you can do typecast like this, that which kind of type you want. From integer to float you can convert, from float to integer also you can convert. Of course it should not be decimals, right? So if it is a decimals and all, then it might trim it off, like, or maybe give an error, like let's say 1.3 to 0.4. So this is currently in floating points, but now let's say you wanted to have a numerical, like D type as integer, that you can do using a dot or torch I don't recall it actually. Change the D type of A to 32. Okay, I guess this is not the way to do it, or maybe you can mention A here, like this, and then into B. So you can see you should want copy construct from tensor. It is recommended to use this is different thing. This has nothing to do with it. I'll explain this part later on. What are these errors? It's not about other thing, but you can see it has converted to integer 32, but now the decimals, right? 1.3 has gone, or 2.4 has gone, something like that. So integers being so now we are losing some values here. So be careful when you do this data D type change, right? So this D types you should not change if not required. Okay, but whenever you create the tensor, just go with the float 32, as this is the most supported data type. Just remember that whenever you do use float 32. Okay, the crux of this discussion is that. Now what you can do is something like empty tensor you can create. For example, let's say C, and you want to create an empty tensor. Now why do you want to do empty tensor is, let's say going to store the gradients of the network. So this gradient initially are empty, right? When you do the back propagation, then it will get filled up. That some gradients are appearing. So initially you don't want to create. You can create zeros. That is there, or you can do empty also. That is also okay. Sometimes you don't want to give any value to it. Even zeros also you don't want to give. So sometimes zero could be issue. Like For example, 0 can so if it's 0, you can do matrix multiplication or something like that, but if it's empty, maybe it's not possible. So here what we're going to get is empty tensor. So it will create a space inside the memory, and but there is one issue, or you will think there is an issue, that it will give you some garbage values which are being stored at the empty tensor location. So that is going to be garbage values, which you don't have to worry about. So let's say you have to write empty. Then what is the dimension you want? So let's say 2 cross 3 means 2 rows, 3 columns. You can do that. And this how C. Okay, not like this. Torch dot tensor 2 cross 3. Torch dot tensor, let's say 1 comma 2. So this 1 comma 2 comma 3 is a value. It has nothing to do with torch dot empty. Maybe I'm making a mistake. Torch dot empty, like this. Okay. This. Okay. So you can see I have created 2 rows, 3 columns, and that is fine. Data type not required, but this all values which are coming here are the garbage values which are being stored at the location which is where this C is present, right? So you can do like ID C. So this is the ID of the C where it's being located. So this location and all is, you don't need to worry about it, but this is something you can find it
Sir,
somewhere.
is it like a C in C or C++ programming?
Correct,
When
correct.
we assign any integer, we initialize an integer, it gets some garbage value.
Yes, kind of like that. So something is being stored in the memory and you get that as of now, but it's currently empty. Like you can store or you can replace these values with something else. That is the idea behind it.
They are random values, right, sir?
Yes, yes. Similarly, you can do torch dot zeros. So let's say you want a matrix of zeros only, right? That you can do. So anything you can give, right? So 2 comma 3 or anything like 3 comma 4. So these are zeros you will get. Similarly, you can get ones. So these are basic metrics which you might require it. Sometimes you want to have zeros and ones or other binary numbers, right? Might be useful to create. Let's say 4 comma 4, anything. Correct. So this is how you can create this thing. Yeah. So now let's say you want to create random numbers. So how will you do that? So that you can do torch dot rand, and of course you have to give what is the dimension you want, right? So say 3 comma 4, and now we'll get random numbers. So this thing will be useful when we initialize uh, the weights. Okay, so weights are being initialized randomly, and that's what is being useful. But don't worry, it's like the thing which we are going to use will not have weights initialized randomly, but it has some methods to initialize the weight in a better way, right? So if you remember the concept that the weight initialization is also an important factor to the later on we'll do um, this convergence, right? So convergence does depend on the weight initialization, and like for now you can think of that if you want to randomly initialize the weight, you can do this way. So this random numbers you'll get right now. If I run it again, you'll see the numbers are changing, and which I don't want. Sometimes I want to freeze them, like whatever, give me random numbers once, but whatever you give me, please don't change it later on. So that's what we can do using manual seed. You would have heard of random seed in NumPy. Same thing here. It's manual seed. So you have to write like torch dot manual seed and give some number like 0, 1, 2, 3, 5, any kind of number. 42 is a popular one. You can give that, and now the weights are free. So if I run it again and again, though weights are randomly initialized, they'll not change unless I change this manual seed value, right? So let's say t whatever. So now they are different, but will stay consistent as long as I use same manual seed value. Okay, right? So that's what it is. Now arrange is something you want to do. Let's say,
So what if like you need to have two variables, so each one needs to be different, so you have to keep changing the manual seed every time you call the number.
so you're saying you want to create two
Variables.
arrays.
So first one is like kind of fixed for this one, and second variable could be maybe it is in a for loop or something like that. So first one is fixed, but because first one is fixed, the next one need not. I'm just asking. There would be a scenario like that.
That could be, but I never encountered that scenario as of now.
Okay.
But if still you want to do, then maybe you can remove the manual seed. Why do you need it? But you want to initialize in certain ways. That
Yeah, for one, maybe I need to have the manual seed, and then later, probably it doesn't make sense to remove it later also. So, yeah, I mean, it's okay. Just asking.
Means
okay.
manual seed like a predictive outcome, no? Just
Yeah,
like in
once you fix
MLT.
the output, then nowhere else in the code I mean, you
Uh,
need, yeah.
that is not the case. So this collab has changed its structure, how it works. Now let's say I set manual seed here. Still, if I run it here, it will give me
Say,
different values
oh, okay.
unless I again mention it here. So if I do this,
This is what I want to know. Yeah. Okay.
so then it will stay consistent.
So if you put the manual seed, only the first time it will create the same.
For the cell which is being written, for that
Okay.
only it will be
On the
like
same
it
seed.
will
Okay.
work.
So
I
what
think
is
it
for
is.
the Python
I think
programs?
it is like 42. First it is 42, then it comes 43, then it's come 44, and when you set 42, then it start from 42, then 43, then 44. Maybe I'm
Uh,
guessing. Maybe it.
no.
You
So
can
once you
try.
mention here, this will work for only cell, only uh, for this cell, right? For next cell, you have to again mention the manual seed. So earlier when collab was Jupyter notebooks was there, then the cells were kind of connected in this way, but now they've done something different, and now they are not. So if you want to create
So can you, sir, write on the first cell again torch dot rand 3 comma 4.
here, right?
The first cell again means in the first cell. Yeah.
Yeah, here
Again.
no. For both of them, it will work. See,
Yeah.
for both
Just
of them,
write
you will
torch.
get same thing.
No. I am saying, sir, write again. Yes, sir. Can you run it again?
But it will give the same output.
No, sir. It is different.
Okay.
Can you write for
We need to print
51?
both lines again. I
In
think we can
51,
print.
can you write, sir, 43?
Okay, you
So you have to print all the 3 lines to see if it works.
okay. Okay, no issue. We can do that. So let's see. This is B. This is C, and now I'm printing C then B. Okay, so if I run this, it's 88, 86. then it's a little bit different.
Again, if you run it, same thing will come for all three.
Yeah, that is correct.
Yeah.
But
So, sir, it is going from 42 to 43 to 44, something like that. Maybe you can try to print with 43. It will match the second part.
So,
okay. 43. It's not matching with 43.
Okay, so it has some random things, sir.
Yeah, it could be. Okay, so it could be anything. Okay. Now we'll look at this arrange thing. Like, let's say you have some values, and so you have to give start number, end number, and what is the step size you want. So maybe 2, 3, 4. You can choose step size, and it will give you that numbers. Right. So like so 0, 3, 6. That's what the step size is, and it ended at 9. Now lean space is something you can do if you wanted some numbers between a range, and it should be equidistant to each other. So the how many numbers you want, that you have to mention. So you have to write like torch dot lean space. Let's say initial value could be 5, and let's say 20, and you want how many values you want in between them, right? Let's say 4 values I want, and they should be equal. So they will be equidistant to each other, like 5, 10, 10, 15, 20. And you can see both are inclusive here, and here I guess 10 could be inclusive. Not sure if I do this. Yeah, 10 is not inclusive, right? So here, but here it is. You don't need to remember this. Just it is there. Okay. Now maybe you require to create a identity function. So you can see the torch.i same as np.i. This function, or even this all thing, arrange, lean space. So this manual seed is a different name, but it works in random seed in NumPy. So this is where it is kind of, you can see, matching with the NumPy codes, and that's what I said when that the torch is kind of related to NumPy. Okay, so this how you can create a identity matrix if required. Now let's say you want to create a torch dot a diagonal matrix, right? So how will you do that? So you have to give some tensor in this vector to be.
Sir, NumPy also create the matrix and vectors, so that are same thing means in the torch, right?
No. So the difference which is there is the tensors will have automatic differentiation, which is not there in the NumPy, and we can move this arrays to GPU using this torch, but that is not possible using NumPy. We can't move this tensor to GPU. So that will do. We will see how. Where is it? Yes. So the tensor computations operations on GPU, like how to do that. We'll do that. So that is the difference between tensors and matrix array. NumPy array, torch and NumPy array. Now some values you can give, let's say 2, 5, 7, anything, and you want them in diagonals. So that's what it will do. Will give you like this, like diagonal. Might be useful when, I'm not sure, but it could be somewhere you might require. So you can do that. Now full is there. So it will fill the whole 2x3 matrix. If you create a 2x3 matrix, and all the values will be 5 of that. So you can see kind of this torch dot ones like this, and you have multiplied it with the 5. Okay? So if you want a different kind of values, you can use the full function. So for example, I would have write 1, and that was the similar thing as torch dot ones, or 0, then that's what it is. But I want different values, so that I can do using full. Now, yeah, so I guess I explained this data type earlier. So that 3264 are long, 232, 264. This is all different kind of data types are there. I'll not go again into this. Shape. So we can do a little bit of reshaping and all. Let's do that. Now let's say I have a tensor. It's a T1 torch dot tensor. Now I have, let's say, T. Let's say I have a matrix. So 6. So it's 3 rows, 2 columns. Let's take one more. Okay, so this is yeah. Now T1 looks like this. We went with the dim function, I guess. T1 dot. That was ndip, but here it's dim. I guess both are same. So there's nothing different about it. Same thing, but it's it. Now you want to reshape it. This is important that you might want to change this. So currently this is say 4 rows and 2 columns, right? 4 cross 2 matrix. You might want it as a 2 cross 4 matrix. So that you can do. So you have to just write T1 dot reshape, and you want 2 rows and 4 columns. So it will do that, right? The only thing you have to be careful here is that the dimension or whatever happens after the reshaping should match with the previous dimension. So here it is 4 cross 2 and 2 cross 4 is possible. So this multiplication is currently 4 into 2, 8. So I can maybe do 2 cross 2 cross 2 also. That is also not an issue. It will give me this 2 cross 2 cross 2 tensor since dimensions are matching. But I can't have like maybe 2 cross 2 cross 1. This is not possible, right? So this is the input. So size is 8. So you have to give that thing. Now you wanted to flatten. So this flatten will come up in CNN when you have the CNN architecture, and the last layer you use is flat layers. So that the tensors are there, you want to flat them. So how will you do that? Is you just have to write T1 dot flatten, and that's all. So it will flat it. So you can see it will give you a vector. Okay, so all of them are in the same thing. So this is what flattening is. Now one is permutation. So this permutation is,
excuse me, sir.
yes.
Can we only flatten 2D tensors?
No, it will flatten 3D as well. You can do that. So let's say
All right.
I have,
So arbitrary dimensions can be flattened out using this function.
yes, got it. So
Okay.
let's say if I have torch dot rand, let's say 2 comma 3 comma 5, right? So I guess I'll get you can see this is very weird. V5 columns and 4 rows, then 3 like that, and 2 on top of that. So this is a 4-dimension tensor. I've stored as a mat. Now should not. Let me reduce this little bit dimension so that we can actually see this. Now yeah, okay, now it has become a little bit manageable to see it. If I do this mat dot flatten, right? So it flattened it. You can see this values are flattened out. Okay. It can be possible any dimension. Any doubt?
So could you just do it using 3 2 3 2 circles? It is very I couldn't visualize it. Yeah, 3, 2, 3, 2. I think that would help. I think.
This you want to flatten it. So that's been flattened, right? Uh, so basically, if after flattening, you'll get a vector. So whatever is there, it will just have it in a one column or vector. You can think anything, row or column. Now there is something called permute. This permute is nothing but uh, let's say you have 2 cross 3 cross 4 dimensions. So this is a dimension I'm mentioning. Tensor, right? So this is a 2 cross 3 cross 4 dimension tensor. Now you wish to change it to, let's say, what 3 cross 2 cross 4. That you can do using permute function. So it will nothing but you kind of say kind of changing it, right? So permutation, right? Like how the permutation matrix works in, if you remember, for MLF kind of thing, that you interchange the rows, interchange the columns, like that. But here you are interchanging the dimensions of the matrix or tensor, right? So that you can do using permute function. So let's say if I use this met, right? So this okay, it will be difficult to show 3 to 3 2, but I'll use some different, like 2 3 4, and this is my matrix. Currently this, it looks like this. Now I want to do torch dot permute. I have to give first met, and let's say I wish to use the dimension of my third position as the first one. So I'll mention that here. So this 2 means the index wise I have to write. Okay, so second is the index at which the 4 is available, and then I can mention 0, so that is there, and then 1. Okay, so what I'm going to do is I am saying that change my matrix, this is met variable, to 4 cross 2 sorry, 3 cross 2. So that's what I'm saying. So initially this is, here it is 3 cross 2 cross 4, right? Now change it, or the permutation, or kind of do that kind of shift, so that it will be 4 cross 3 cross 2. That's what I'm saying here. And if I run this, so you can see now I have so the same values, like 0 0.3125, 0 0.313013, same thing, but now it is like this, right? That's what you can do using permutation. Another is squeeze and unsqueeze. So this permutation you might not use much, but the squeeze and squeeze, that is important. This you will use several times to do it. So this one importance of this function is when when handle image data. So that's where you'll get outputs in let's say 2D or 3D. You might want to change it to 1D as a vector, then you can compare with the labels or something like that. So that squeezing you have to do of the outputs, or sometimes you have some output but you want to unsqueeze it. So that's what you can do here, squeezing and unsqueezing. So unsqueeze will do, let's say I have mat torch dot unsqueeze. So let's say matrix is what I'm using. So this is matrix met, and then you want to squeeze it. So which dimension you want to squeeze it, right? So I'm mentioning 0. So this will be squeezed out, like the 3 will be squeezed out. Yeah, something like
What does squeeze and
Sorry,
unsqueeze
this is
means?
unsqueezing. We are expanding it. Let me show you with squeeze first. That will be better. So let's say you get generally you get it as outputs as 2D or something. That's what you will see. So let's say I have torch dot rand, and I have one. Uh, just like this. So you can see this is a vector, but it's a 2D of this, right? So now I don't want this another dimension. So what I'll do is you can write b dot squeeze it. So the squeezing will happen here, or I should write torch dot squeeze squeeze this b. So it will give me one less dimension. So it will remove one dimension from this. That's what squeezing is. Now unsqueezing is the opposite of that. So this unsqueezing will be not much useful, but the squeezing will be useful. Like you want to squeeze something. Unsqueezing, let's see what is.
Squeezing is in a sense reducing any redundant dimension.
Yes, you can think of like that. Right. So let's say return tensor with so if you wish to read first about the squeeze, let's do that. So with all specified dimension of input size, one removed, right? So one dimension. So let's say, for example, if input is of shape A cross 1 cross B cross C cross 1 cross D, so then if you do the squeeze, the shape will be A cross B cross C cross D. So this one will be removed, both of them. Right? So this is what squeezing will do. So whenever you have, let's say here we had 1 cross 5. So that's why this one got removed and you have 5 now. So if I have, let's say 1 cross 5 cross 1 like this, then also again like it will do same thing, right? So all this ones will be removed. That's what the squeezing operation is. Okay. Like that. Like let's say I have 3 here. So this is a little bit different. Now if I do squeezing, I'll have 5 cross 3 something, right? So you can see this is 5 cross.
So I have one doubt.
Yes.
So the permute method, is it the same as transposition, performing a transposition on a tensor?
Could be.
Like in like for 2D matrices, what we do, like when we perform a transposition, we swap the row space and the column space of that matrix, flipping it across the diagonal.
No, it is kind of like that, but not like that. So we'll not do the row replacement, right? Like what we do in when we solve this matrix and when we are maybe finding this row echelon form or something like that, where we replace the rows with R1 to R3, something like that. That is permutation there, but this is little different. Here we are kind of changing the dimension itself. Like let's say initially we had 3 cross 2. Now you can make it 2 cross 3, or let's say you have 2 cross 3 cross 5, but you want 5 cross 2 cross 3. So that kind of transformation you can do.
Okay,
so
sir.
Here, see, initially we had 3 cross 2 cross 4, but we wanted 4 cross 3 cross 2. So this transformation you can do using permute function. Okay.
All right.
Yeah. So this is what squeezing is. So wherever one dimension is there, you can remove it. Now unsqueeze. If I do that. Yeah. So here, with the dimension of size 1 inserted at a specified position there. So here it will add one more dimension to it, right? So let's say it is telling me to add at 0th position 1 dimension. So it will add that, or you want it at the 1, 2, like I mentioned here. For example, here, right? So if you have 5 cross 3, which is this, let's say I call it as C. Which I call this as C. Now if I wish to add one more dimension to it, I can do using C dot unsqueeze or torch dot unsqueeze C, and add it at the 0th thing. So the 0th means this guy. This is 0. This is 1. This is 2. This is 3. So all these possibilities are there. And if I do that, there is one more dimension added here. You can see this is 2D now. Now, what if I do? Can I add it at 2 places? Not sure if we can do that. So this is at least like for one thing you can do. Maybe not possible that you can do unsqueeze at 2 places. Okay? So this is how you can do unsqueezing. But remember, the squeezing will be more important. This will use somewhere. Unsqueeze, I'm not sure. I will not use for this workshop at least. Random. So as of now, the important functions which you should remember is, one is this tensor, torch.tensor, how to create a tensor. Then how to find a shape of it. Okay, so the shape and all will be important. Float 32, that's what you should remember, and long also you should remember. Now empty, that is okay, you don't need to remember any of this. Maybe manual seed, so this manual seed and random function, this you should remember. Another thing is arrange, not needed. Diagonal, nothing. Reshaping, so this reshaping function, do remember it, that how to do the reshaping of it. Flattening, definitely remember it, how to flatten something. And then not needed. Squeezing, or yeah, so the squeezing part, do remember it, unsqueeze not needed. So as of now, these are the important functions which we have covered. Okay, now what else we have? We have a lot of the things, but okay. So I'll just explain this now a little briefly, and then we'll move on because not important much. Now let's say you want to create another tensor which should have dimensions of some tensor, right? So let's say you have T1 torch dot tensor, which has or let's say torch dot rand, let's say 2 cross 3, 2 cross 3, like this is the dimension of T1, right? Now you wanted another matrix and another tensor which should be empty, but it should have dimension of 2 cross 3. For some reason, the dimension of T1 and the another matrix, another tensor should match. That is the whole idea of this. So what you can do is you can write torch dot empty like T1. Okay. So this will be empty. Some garbage will show up, but it is empty, and it has dimension of 2 cross 3. That is the empty like. So all this similar shape tensors, empty like, zeros like. So now if you want all of them as zeros, that you can do. So if I like, just copy paste few things. Okay, so you can see all of them 0, but dimension will be similar. So this similar dimension. So the idea of similar dimension is when we store the gradients, right? So if you remember, all the gradients will have gradient. If you store all the gradients in a matrix, it will have similar size to the weights. So let's say weights were in 3 cross 4. So the gradients will also be, if they are in 3 cross 4, that would be great, right? So this operations of subtracting will happen easily. So that's why these are there. Will most likely not use it, but that is there, because the way we are going to define the ANN and all, it is automatically being done internally. So we don't need to do it. If you want all of them to be filled with ones, you can use ones like, and then random like is also there. So this will give you some random numbers here with the dimension of 2 cross, right? So that whatever tensor you mention here inside this like functions, the dimensions you will get from that, right? So this will give you the dimension, and then whatever zeros, ones, empty, whatever that you will get. Now, few operations you can do. Let's say you have tensor torch dot tensor 2. So this is a, and then b is also there 3. So you can do a plus b, right? So this is scalar addition, or you can actually do, let's say, torch or say b plus 5. Right? So this both kind of scalar additions you can do. Scalar subtraction you can do, let's say b minus 3, b minus 1. And so this all operations are possible. So you don't need to, if mention another b or another a as a tensor, and then only you can do subtraction. You can directly do it as it is. And this a and b are also scalar tensors, right? So these are scalar tensors. This is just scalar value. So both the ways it is okay. You can do this way or that way, but generally we prefer this, right? Why should I create another tensor for doing some like subtraction or addition and like that, right? Or let's say if I wanted to multiply b with 2, you can do that. If I wish to divide it with something, I can do that. So you just have to write this, and you can see it is scalar division. So here I get in decimals. If I use double slash, say like this, then that will give me the integer value, right? Like the integer value that will be float, and this is like total division, something like that. Now, if you wish to have remainder, so this is pure Python, like you would have done in Python. And what will be the remainder I get? That you can have it like this. Power you can do like double stars. So double stars will be used for power, and this kind of scalar operations you can do. Now, few element-wise operations. So this element-wise operations, if you remember, we do in GRU LSTMs. We do this internally. So to make those architecture, we require this, right? So that's why it does exist. And what you have to do is, let's say I have a matrix. Let's say tensor, sorry, torch dot tensor torch dot. Can you mute your mic, Jitesh? If you don't have any question. All right, thank you. Okay, torch dot random. Let's say 2 cross 3, and let's say I have another tensor, which should also be of similar size, right? That is the idea of that. So torch dot. Would wait if I do create manually. Say I have 1, 2, 3, and I have 6 ish. So, and another tensor is say 1, 1, 1, and right. So we have 2 tensors. Now we can do T1 plus T2, and that is element wise addition. You can see 1 plus 1 2, 2 plus 1 3, 3 plus 1 4, and similarly like that. You can do all of them multiplication, like T1 star T2, and here it is like it has increased by double, right? And when we get out absolute negative round and all, so yes, absolute if I would have any negative, that would have made sense. Like so let's say if I have -1 here, let's say -6 here. Now if I do, you can see I am getting absolute. Similarly, I can do negative. Yes. Not sure if that is a function. Right, so all of them got negated. You can do like torch dot add also. Okay. T1 comma T2. Yes, right. So this both are same. Like if you wish to write the function, that is also okay. Now ceiling, flooring, clamping, so clamping is something you wish to clamp the values between a range, right? So let's say you have torch dot tensor. Let's say I have values from -5, -2, 0, 1, 2, 3, 4, like this. I have storing it in, let's say, T3. Okay. Now let's say I want to clamp it. So generally we do clamping when we have gradient descent. We don't want to have gradient exploding. Right? So this gradient explosion you can stop using clamping. So you can write like torch dot clamp, give your tensor, and then what is the minimum value that you can mention. So let's say minimum should be 0, and let's say max should be 2, something, anything, 1. Then you can define that, right? So if I do that, so you can see the here clamping happened. So that's why this negative values are now 0, and whatever is more than 2 are being now used as 2. So maybe this is useful in ReLU also. So let's say you don't define max, it works as a ReLU, right? So this is, you can kind of think like ReLU also, but will not do ReLU because differentiation would be, but could be possible to do differentiation of this. Depends like how it's been written, but will not do this way. There is another function being created for that. Okay. Now some statistics you can do, like let's say T1 dot sum. If I do, so my T1 is this one. So this is my T1. If you want to sum all of them, I can do. So you can see this is 5 plus 5 10, 10 plus 4 14, 14 minus 7, which is 7, right? So this is correct. So summing. Now sometimes you wanted to wish to like sum across the axis, like, right? So that you can do. This x is equal to 0. So the summation is happening across this columns, right? So -3 plus 4 is 3, 2 plus 5 is 7, and then 3 minus 6 is -3. And another could be, you can write 1. Okay. So simple, you would have done this using pandas or numpy. You would have done this sometimes, right? So, and then let's say you wish to find a mean of this, you can do that. And could not infer output. Input type must be either floating point or complex. Got long. So you can see the error is due to this. These values are not a float, so this mean is not working. Okay, so what you can do is you can do T1, or maybe you can create another variable. Let's say torch dot tensor, then let's say 1, 2, 3, or 4, whatever, 2, 6. Then you can mention D type is equal to torch dot float. So by default it's 32, so I don't need to mention that. Now I can get the mean. I missed this part. Okay, so this is a mean of this all values. Of course, this will works across axis also. So if you want to write x is equal to 1, that is also possible. Similarly, you can do median of this, right? So this is the median of that. You can do max of this. You can do min of this. Now you can do standard deviation of this. Argmax, argmin. So this argmax and argmin are the function. What it gives you, it will give you the index which has the maximum value. It will not give you the value, but it will give the index of that. Okay, so t2 dot argmax, if I do so, this is it's saying fifth. If I see in t2, the fifth could be this 0, or no, it should be this. So it should start from 0 to 5, 0, 1, 2, 3, 4, 5. That then I have again arg min, so which will give me 0, I guess, right? So in t2, this is the position where the minimum value is there, so give 0. Okay, so this something like that is there. Now matrix, okay, matrix multiplication you can do. So let's say I have tensor 1, which is this, and I have tensor 2. I can't do matrix. Can I do matrix multiplication here? So I have 2 rows and 3 columns. So this is 2 cross 3. And here I have 3 cross 2. Yeah, I guess it's possible. So I do T1, something like that. So if I do torch, dot mat level. So this function also similar to NumPy. I have to given T1 comma T2, and the matrix multiplication you can get, right? So this is what you get from that. Of course, you can do dot also, but to do the dot, you need vectors, and this vector should be of same size, right? That's how the dot product works. Between two vectors, you can do the dot product, right? So like this, and then you have to write torch dot T1 comma T2, and that is right. So dot product is similarly like 4 into 1 plus 2 into 5 plus 6 into 3, right? That's what dot product is, and that's what you are getting. Transpose you can do, let's say I wanted to do torch dot transpose, or I guess I can directly give T1 and do the transpose of that. Okay, so the issue is that is we are giving a vector. It should be a matrix, right? So that is the issue. If I do this way, no, what is the issue? Torch dot transpose. So T1 dot. T1 composite. Okay, fine. Okay. So just read about it. So if you feel confused, what is it? Like sometimes nobody can able to remember this many functions. What are they? You can read about it. What does it do? How does it work? Right. So generally do that. No need to remember this. You can similarly able to do determinant, inverse, something like that. Right. So this all things you can do. Now, okay. So some things like comparisons, which we generally do when we learn any. So this all functions which we are looking at as of now. Why we are looking at is to get familiarized with Pytorch. First thing is that these are the basic operations which we generally do with any programming language, right? We do element wise operations or operations, mathematical operations we do, right? Shapes, tensors, the basic unit of this Pytorch is tensor, so we've spent a little time on that. And now we are going to do statistics. That's what we did also, right? Matrix operations we did. Now comparisons is the next part. Like how do you compare two metrics? You can do that. So greater than, less than. So similarly, you have to use the symbol. That's all. Like let's say I have to one equal to torch dot tensor. Like this, and let's say I have another tensor. Which has values like say 5, 0, 7, something like this, and I'll call it as T2. Now, if I ask, is T1 greater than T2? So you can see here it's false, here it's true, and true, false, right? So similarly, you can do other way around also, like this. So these are the comparisons you can do. Okay, it could be useful. So equal to, so you can do, right? So this less than, greater than, whatever you call this, any of them, whichever it is, that you can do. Now some important functions are like logarithmic. You want to do like a torch dot log functions. You want to apply on all the values of T1. You can do that. So here you can see this is T1. And I applied log on that, and log of 1 is 0. So that's why the first value is 0, and then some values are appearing. Similarly, you can do torch.exponential using this. Similarly, if you want to square all the values, you can do that. Okay, so here we are doing square. You can do square root also. Right, so if I do square root, I will not get much good values, but this is square. Right, so if you remember, square root of 2 is 1.41, right? That's what it is. Square root of 4 should be 2. Like here, right? So this is square root of 2. Sigmoid function we can now look as of now. So the sigmoid is what you do for 1 by 1 plus e power z. Here is the value that is being given here. So 1 T1 is mentioned here. So 1, 2. So what we'll do is we will do 1 by 1 plus e power 1. As of now, e power 1 or minus 1, right? So minus z is the formula. So e power minus 1, then we'll do e power minus 2, then e power minus 3, and then so on. So for each of them, we'll compute that value using sigmoid, and that's what we'll do. And you can see this is the value you are getting, right? So let's say if I write a function, find sigmoid, and let's say if I'm giving a input as some tensor, right? That's t. I'll call it as t. Now, what I have to do is I have to return. So we did element-wise operations, right? So 1 plus torch dot exp and minus of t, right? So that's what we are doing, and that's what the sigmoid is. So if I do, let's say find sigmoid of t1. So you can see same thing. That's what we did here using sigmoid, and similarly softmax, whatever the softmax formula is, you can definitely check it out. That's also we can do using this. Now here the thing is softmax expects a vector, right? So I don't think so it will work on metrics unless I mention a axis or something. But let's check. I am not sure. So I guess I have to mention. Okay, so the issue with T1 is it's giving long, but it is expecting floats. So you can see another error we have come across. So this T1 will not work. So softmax is expecting that value should be float, right? So we will do that. Say d type equal to torch dot something like that. And now if I do, you can see the softmax is working there. Received an invalid combination argument, integer dimension, something. And so you have to mention the t dimension. That's what I said. That it is expecting to have a vector, and from that it will predict the class of it, or predict, or it will do apply the softmax over it, right? So that's what you have to mention it. That which dimension you want, or like I think axis will work too. Same thing, right? Axis or dimension, you can try it out. They both are similar thing. Right? So like this, if I write dim as one, same thing. So anything you wish to use. I generally prefer axis because earlier when we did sum and all, that's what it is. Same thing, like whatever we did in sum. Where is it? It should be, yeah, here, right? So the sum then x is equal to 0 and 1. Similar thing we are doing here, that we are mentioning that kind of consider one dimension as a vector and then do compute the softmax computation. Okay. Now ReLU. So you can do this. So as of now, all of them are positive, so it doesn't make any difference. But if I have, let's say, -1 and let's say -4, now you can see both of them got 0 because that's what ReLU does. It if it is positive, then it let it be whatever value is. If it's negative, then it will clamp it to 0. Okay. So these are few things. Okay. So now we have half an hour left. How much can I cover now? So the next thing which we have is in place operations. So what does in place operations does is, like let's say you have let's say you have matrix and you do let's say you have A, which is a tensor. Okay. Now B is also another tensor. Okay. Let's say 4, 5, 6, something like that. So as of now, I'm explaining this in place operations. Now let's say if you do A plus B, you're getting this, but you have to store it somewhere, right? So what you will do, you will do C equal to this, and we are using another variable to store the summation of it. But by some chance, like by some reason, you wish to add it, but you don't want another variable to it. One possible scenario is when we do weight update. So let's say I have weights. Let's say I have weights which are like this, and let's say for some reason I have gradient also, which looks like this. Okay. Now my let's mention this as W1, this as grads. Okay. So for some reason I computed gradient, I got this. Now I wish to update my weights. So the idea is I want to do this by some learning rate, definitely, but let's not do that as of now. So this is what I want to do. Select this, right? So this is what I want to do, but I have to store it in another variable, which I don't like. So what I wish to do is I want to do in W itself, like this, something like this. So another way to do is you can do VW dot say subtract, and you can use this. You can see what do you call this? Underscore, right? So underscore you can use if you do that. That's called in place operation, and you can mention grade here, and that's all. So same thing, whatever I did earlier. So that's why I have to write it differently, but here in place operations are there, which you can do here this way. So they are easy. Another thing which you wanted to do later on is you want to replace all the gradients with 0 once a cycle is complete. So after epoch, you want to reset the gradients to 0. So that you can do. So if you do like W dot 0, right, so it will do that. So now you can see all the pages got 0 here. We'll use this. Don't worry. We'll go again with this. How to do this in place operation. So the 0 part will again definitely comes up. So this remember that. Okay. Now cloning, right? So cloning is important. So let's say if you have A, which is this, and let's say if I do B equal to A, and if I show you ID of A and ID of B, you can see the B is also referencing it to A only, right? So both of them have same ID. That means if I do any changes in B, let's say now if I do B, let's say B dot, what should I call? Yeah, B dot add 1. So now it's adding 1 to each of them of B. And if I show you what is A, you can see A has also changed, which it should not, right? A is just 1, 2, 3. B is what I made some changes to, and it happens in such a way that even A got changed. Why? Because we said A B equal to A. So this is not the way to copy the A, clone the A. So the another way is what we'll do is we'll write B is equal to because dot clone of A. Okay, so if you do this way, now B is different, and if I show you ID of B, you can see whatever 4, 5. Like now you can see the last few element. If you see 0, 5, 6, here it is 4, 5, 6, right? 1, 3, 7, 1, whatever. So it looks like initial one are similar, but you can see from the last that it is different. So now it is a different variable. Now even though if I do, for example, this is my A. ID of A is this. Currently, this B is coming from here. Now, if I add, it will change my A also. Now, let's say I'll just mention it as C, right, which is a clone of A. And ID of C is different than ID of A and B, because B is just a same thing as A. Now, if I do any C dot add, so again I add 1 to it. So you can see 3, 4, 5 is the value. If I show you the A, it has not changed, right? So on the other hand, when I did equal to here, it did change to the A. So we don't want that sometimes. So just make sure that whenever you do the copying of weights or any matrices, anything vectors, you should use clone, not equal to. Equal to will not do that. If you make any changes to B, it will eventually comes to A also. So they are linked, and we don't want that sometimes. So use clone. Okay, so now we are actually moving to the GPUs, and that's where I'll go there. So now I'll just connect it to GPU. Before that, any question? I'll just give some. Okay, I think class was supposed to end at 10:30. That is correct. I kind of thought it's 11. So okay, so we'll do auto grade tomorrow. This auto grade part we'll do tomorrow. Today we'll look into this part of how does GPU, what we can do with GPU and all. I'll just show you the GPU, and that's all. We'll close it. We'll not do much with GPU today. Okay, so what you have to do is you have to change the runtime type. Go to T for GPU, save it. It will reconnect it. Again, you have to import the torch. So I can go to the first cell and do it, but I'll just do it here. Okay. So just so I let you know that before connecting to GPU, if you would have run this torch.cuda.device count, it would have showed 0. But after it's getting connected to T4 GPU, it will show count as 1. And this function, which torch.cuda.get device properties. So if you don't have any CUDA device, the CUDA device is GPU, then that will show this error. So found no NVIDIA driver on your system. Please check that you have NVIDIA GPU installed, a driver from this website. Okay. So if my notebook gets connected, which it did, now you can see I have T4 this thing, right? So you can see now I got GPU here. It's a T4 GPU. We can see now if I run this cell torch.device count, which is 1 now from 0, and earlier the error was I didn't run this. It's like from the previous thing. So when CPU was connected, not GPU, and you can see it's giving error. Now it has shown some properties of this. So name is Tesla T4, major minor of that, total memory is this much, 15095, that is 15 GB approximately. How many count processors are there? 40 processor counts are there, right? So this all things are properties about CUDA device or GPU, as being shown here. If I run this, just same thing.
This GPU is more powerful than normal laptop GPU, which comes in 1 to 1.5 lakhs range.
I'm not sure. You can check this, like you can maybe run it in your Jupyter notebook. then only you will get to know that is it more powerful than that. But I don't think so. It is. So so like you have to check what is the major and minor here. So if you have that major and minor, that will actually define what is the compute capability. So here it is 7.5, but if you're higher than this, that means you have better GPU. Okay? So whatever it is, you can run this. Even of course this multiprocess counter, if that is also high, that means it's good. This is just a memory. I think now GPU should be 8 GB to 16 GB should be there in your laptop. If you wanted to use the GPU for this purpose, otherwise Colab is good. Right? Now, if you run this tortured device, so now what is this? Like okay. So if you have multiple GPUs, some people has it like multiple GPUs are there. You have to index it. Which GPU you want to use? 0, 1, 2, 3, right? So that's what you have to do. And how you can do is you have to mention tortured device. Type is CUDA, of course, and index you have to mention. So as of now, we have only one GPU. So index 0 is of course sufficient. But if you have multiple GPU, you can mention what is the index 1, 2, 3, whatever. But we don't have, so we have just 0. Okay. So this function, what we'll do is we'll always use this line of code. You don't need to remember this. You can just always copy this, or you can search like how to store device. GPU device and a variable, and it will any kind of code will show up, not this particularly anything. So the thing is, if tortured CUDA is available, then write CUDA else CPU. So we just wanted to know which kind of device we are going to use, right? So that's what we'll do. So you can see now we have actually CUDA available, so it is going to say that device is CUDA. And whenever you create a tensor, so earlier we did create a tensor. Where I didn't mention, but if you wish to compute it on the GPU, you have to move it to device, or you have to create it in the GPU. Okay? So this creation of tensor in the GPU is by like this, like you have to use device equal to device, and currently the device is this CUDA. Okay, CUDA GPU. So that's what we are doing, and you can see this is a little bit different, right? So if I don't do that, let's say if I don't mention any device, you can see by default it is not coming up. That devices is CUDA 0. Right. So this is a normal tensor, or you can say tensor in the CPU, but this is the tensor in the GPU. Okay, so that's what the difference is, and you can try it out. So the next thing you can maybe try it out. See here you have no, not here, but you can try it out two metrics, large metrics like let's say 50 cross 50 cross 100 or anything like that, 1000 cross 50 or something like that. Try to do matrix multiplication using CPU, and like this, if you create in GPU, do it in GPU. You just have to write T1 matmul or torch.matmul T1, T2, something like that. You can try it out and you can check it out the time. You will see that GPU is having like very fast computation that you can do. Now, sometimes what happens is this is where we created tensor in the GPU itself, so there is no issue. But what if I have already I already have a tensor created by I don't know whatever reason I created it. I want to move it to device. So how will I do that? So this is way you can move it to the GPU. So you have to write mat 1, 2, just 2. That is the like 2 is the function name, and then you have to mention the device. So device is being this type, which you already stored in the variable here. So this part is being used here, and similarly, this is what going to come up next or tomorrow. That just consider that this is a model which is being mentioned like this. And how do you move a model to the GPU? So the same thing you have to do, model, which is like this, and to device. So if you do that, then it will be moved to the GPU. Okay. Yeah, so that's all for today's class. How to move a model or anything to GPU, that's what we covered last. We'll use this part tomorrow. Definitely we'll use this, how we can do GPU computation and why is it necessary. So tomorrow it will be used, so remember this. Remember a few of the functions, whichever you can as of now. No need to actually like sit and go through that. Remember it. It's not necessary. Whatever you can, that is okay. Okay, because later on when you'll do real coding or when you'll build a project, some of these functions you will definitely be able to remember because they are most likely used and something like that, but you don't have to sit and remember all this. So I just wanted to give you an introduction of this, that this all things just exist in the space of Pytorch, so that it will be in your like subconscious mind that something like this does exist, and if you need to do addition, multiplication, division, empty, in place functions, this all things, the names are familiar to you, right? So this is a familiarity to Pytorch. For that purpose, we have gone through this boring, very boring thing. All the functions are all, but it was necessary.